n greater than 1 be integers. Suppose the product of the solutions for x of the equation 8 log nx times log mx minus 7 log nx minus 6 log mx minus 2013 equals 0 is the smallest possible integer. What is m plus n? If we want to know stuff related to the product of the solutions for x of this equation, then we need to know stuff related to log x in this equation. And we can get that log x related stuff by using the change of base formula. And that's going to give us 8 times log x over log n times log x over log m minus 7 log x over log n minus 6 log x over log m minus 2013 equals 0. We can also write this as a quadratic in terms of log x, and that's equal to 8 over log n log m times log x squared minus 7 over log n plus 6 over log m log x minus 2013 equals 0. And now we can use this quadratic polynomial in terms of log x to find some stuff related to log x. If we want to find the product of the solutions for x of this equation, let's call the values of x that satisfy this equation x1 and x2. So we want x1 times x2. And we know that the product of the solutions for x of this equation is related to the sum of the solutions for log x in this quadratic polynomial in terms of log x I've written over here. So we know that x1 times x2, which is the product of the solutions for x, is equal to x1, which is nothing but 10 to the power of log x1. And then x2 is equal to 10 to the power of log x2. And to see why it's related to the sum of the solutions for log x, this is simply equal to, if you use your exponent rules, 10 to the power of log x1 plus log x2, which are the two solutions for x. So we can use Vieta's formulas in this quadratic polynomial over here to find the sum of the solutions for log x. And that is just minus b over a, which is 7 over log n plus 6 over log m over 8 over log n log m. And if we multiply both numerator and denominator by log n times log m, we're going to get 7 log m plus 6 log n over 8. So that is the sum of the solutions for log x of this equation. And then 10 to the power of that is going to be the product of the solutions for x of this equation. Let's do 10 to the power of this. So we want 10 to the power of 7 log m plus 6 log n over 8. And that's going to be nothing but the 8th root of some number, 10 to the power of 7 log m times 10 to the power of 6 log n. However, this first number is just m to the 7th, and this second number is just n to the 6th, using our log rules. So really, what we're just looking for is that the 8th root of m to the 7th times n to the 6th is some positive integer greater than 1. Let's call it p. So we want m to the 7th times n to the 6th equals p to the 8th. In order to minimize m and n, we need them to both be equal to some power of a smaller integer q intuitively. So let's call this m to the 7th q to the power of 7r, and then let's call this n q to the power of 6s. And then we would like their product to be equal to p to the 8th, which is q to the power of 8t, suppose, for some positive integer t. So this just reduces to 7r plus 6s equals 8t for some positive integers r, s, and t. So in order to solve this in terms of positive integers, we need that 7r plus 6s is congruent to 0 mod 8. And we want the smallest positive integers r and s. So 7r is congruent to negative r mod 8, and 6s is congruent to negative 2s. So if you do that, if you just subtract 8r and then 8s, it won't change the mod 8 value of this expression, because 8r and 8s are congruent to 0 mod 8. So this expression we can say is also congruent to 0 mod 8. And if we take away the negative signs, which we can do because minus 1 is not a multiple of 8, we get r plus 2s is congruent to 0 mod 8. And if we want these to be the smallest values possible for r and s, we need their sum to be exactly 8. It can't be 0 because they have to be both greater than 0, as m and n are greater than 1. So it has to be 8. So r plus 2s equals 8. And if we want everything to minimize, we need q to be equal to 2. Because that's the least integer greater than 1. So we also have r plus 2s equals 8. And this implies that r is even. So r can be either 2, 4, or 6, in which respective case s would be equal to 8 minus 2 over 2, which is 6 over 2, and that's 3. If r was 4, then 2s would have to be 4, so s is 2. And if r is 6, then s would be 1. We can verify that these values for r and s do all give us valid values for t, because if r is 2 and s is 3, then we have 7 times 2 plus 6 times 3 is 14 plus 18, which is 32. And that's equal to 8t, so t is 4. In the second case, if r is 4 and s is 2, that means 7 times 4 is 28, and 6 times 2 is 12. So in that case, it would be 28 plus 12 is 40, so t would be 5. And in the final one, r is 6, so 7r is 42, and 6s is just 6. So 42 plus 6 is 48, so t would be 6. So t equals 4, 5, and 6. Those are all positive integers. Now we wanted to find the smallest possible value of m plus n. And we define m as q to the r and n as q to the s. So m plus n is just q to the r plus q to the s. And to minimize this, we chose q equals 2. So that's just 2 to the r plus 2 to the s. So now it's just left to see which one of these r-s combinations gives us the least value for 2 to the r plus 2 to the s. So the first one gives us 2 squared plus 2 cubed, which is equal to 4 plus 8, and that's 12. The second one gives us 2 squared plus 2 to the 4th, which is 4 plus 16, and that's 20. The last one gives us 2 to the 1 plus 2 to the 6th. And that's equal to 2 plus 64, which is 66. Clearly way too high. The smallest of these is 12, and that is answer choice A. So we are done. Thank you for watching my YouTube video, and please follow my channel if you would like to see more videos.